Hello students, in this session we are going to see about the session of forced vibration. So forced vibration is when the body vibrates under the influence of external force. A body is said to be in forced vibration. We know some examples like ringing of electrical bell, vibrations of air compressors, etc. These are some examples for forced vibration. Next, we should know about the types of external excitations. There are three types of external forces applied. First one is the periodic forces, second one is the impulsive type of forces, and the third type is the random forces. Next, we are going to see about the harmonic disturbances in spring mass system. First is the amplitude H. The amplitude of the forced vibration is given as H is equal to F naught divided by root of 1 minus S minus M omega square plus C omega square into sin omega t minus phi, where F naught is the excited force and phi is the phase lag. Harmonic disturbances for spring mass system can be found out using its max value, that is the maximum amplitude of the forced vibration. Its max is equal to F naught divided by root of S minus M omega square the whole square plus C omega the whole square. Therefore, the value becomes H max is equal to F naught by S divided by root of 1 minus r square the whole square plus 2 epsilon r the whole square, and the r value is the frequency ratio, which is omega by omega n. Therefore, omega by omega n is the angular velocity of the excited force or applied force. Harmonic disturbances, the amplitude of forced vibration is given as h is equal to f naught by root of s minus m omega square the whole square plus c omega square into sin omega t plus phi. F naught is the force excited and phi is the phase lag. The maximum amplitude of the forced vibration is given as follows. First one, phase lag phi. As the displacement takes place after applying force, the displacement vector lags the force vector by some angle phi. This angle is known as phase lag. Mathematically, phi is equal to tan inverse of 2 epsilon r divided by 1 minus r square, where r is the frequency ratio. Second is the magnification factor or dynamic magnifier. The ratio of maximum displacement of the forced vibration h max to the static deflection h naught due to the static force is known as magnification factor. MF is equal to h max by h naught, or MF is equal to 1 divided by root of 1 minus r square the whole square plus 2 epsilon r the whole square. MF is equal to h max by h naught, which is MF is equal to 1 divided by root of 1 minus r square the whole square plus 2 epsilon r the whole square. It is clear that the magnification factor depends on the following two factors: the damping factor and the ratio of circular frequencies. Next, we are going to see about the harmonic disturbances and the characteristics curve. First, the frequency response curve. A curve drawn between magnification factor and the frequency ratio is known as frequency response curve. This curve denotes the eta values, eta equal to 0.02 to 0.05, 0.1, 0.2, 0.4, 0.6 and 1 and 1.3. The values and the amplitude values corresponds to the eta values from 1.5 to 0.001. Second is a phase frequency response curve, which denotes the curve drawn between the phase angle phi and the frequency ratio. Here, the value of eta is varies from zero point 0.2 to 0.02, and the curve is drawn between the frequency and the phase lag phi, which is in radians. The disturbance caused by unbalance. Almost in all rotating and reciprocating machineries like an electric motor, a turbine, an IC engine, etc., we have some amount of unbalanced force left in them even after their correction of precision balancing machines. This unbalanced machines masses produces a exciting force in the machine. The disturbances caused by unbalance is the amplitude of forced vibration X is equal to mu into omega square E divided by root of S minus m omega square the whole square plus C omega the whole square into cos omega t minus phi, where mu is the unbalanced mass and E is the eccentricity. The maximum amplitude of forced vibration is given by H max is equal to m omega square E divided by root of S minus m omega square the whole square plus C omega square. H max by m u E divided by m equal to r square divided by root of 1 minus r square the whole square plus 2 epsilon r the whole square. Next, the phase lag. As the displacement takes place after applying force, the displacement vector lags the force vector by some angle. This angle is known as phase lag phi. Mathematically, phi is equal to tan inverse of 2 eta r divided by 1 minus r square, where r is the frequency ratio. Next is the absolute amplitude. H max is equal to y into root of s square plus c omega square. H max by y is equal to root of 1 plus 2 eta r the whole square divided by 1 minus r square plus 2 eta r the whole square, where y is the amplitude and phi is the phase angle. The relative amplitude. In many cases, it is useful to know the response of the system relative to a moving system. The steady state relative amplitude of the forced vibration is given by Z by Y equal to R square divided by root of 1 minus R square the whole square plus 2 eta R the whole square, where Z is the relative motion of the mass with respect to support and the phase angle phi is equal to tan inverse of 2 epsilon r minus 1 minus r square. Next is the transmissibility, which is the measure of the effectiveness of the vibration isolating material. Two types of transmissibility present are force transmissibility and motion transmissibility. Force transmissibility is defined as the ratio of force transmitted to the force applied on the system. This ratio is also known as isolating factor. It is denoted by epsilon. Force transmissibility epsilon is equal to force transmitted to the foundation divided by force applied on the system. Epsilon is equal to Ft by F naught is equal to root of 1 minus 2 Cr the whole square divided by root of 1 minus R square the whole square plus 2 eta R the whole square. Motion transmissibility is defined as the ratio of absolute amplitude of the mass Ft to the base or support base excitation amplitude y. This ratio is also known as amplitude transmissibility, which is denoted by A. Epsilon A is equal to H max by y equal to root of 1 plus 2 eta r the whole square divided by 1 minus r square plus 2 epsilon r the whole square. The process of reducing the vibrations of the machines and hence reducing the transmitted forces to the foundation using vibration isolating material is called vibration isolation. Some of the materials used are rubber, cork and metallic springs. There are different types of isolation. Isolation of forces. When vibrations produced in unbalanced machines, just should be greater isolated from the foundation so that the adjoining structure is not set into vibrations. This type of isolation is known as forced isolation. Second is the isolation of motions. The unbalanced machines are isolated from their foundations so that there should not be any damage either to the machine or foundations. This type of isolation is known as motion isolation. Thank you.